Lesson: Unsupervised Learning, Identifying Anomalous Network Behavior. Unsupervised learning is a powerful tool in the realm of cybersecurity, particularly when it comes to identifying anomalous network behavior. Unlike supervised learning, which relies on labeled datasets, unsupervised learning works with unlabeled data to identify patterns, structures, or anomalies without prior knowledge of the data's characteristics. This makes it particularly suited to threat detection in dynamic and unpredictable network environments, where new and unknown threats continuously emerge. In cybersecurity, the ability to detect anomalies within network traffic is crucial. Anomalies might indicate a range of issues, from benign misconfigurations to malicious attacks. Unsupervised learning algorithms can sift through massive datasets to identify outliers or unusual patterns that might indicate a security threat. Techniques such as clustering, dimensionality reduction, and neural networks are commonly employed to achieve this. Clustering techniques like k-means clustering and hierarchical clustering are often used to identify anomalous behavior. These algorithms group data points with similar characteristics, making outliers data points that do not fit any cluster readily apparent. For instance, in a typical corporate network, most devices will generate predictable patterns of traffic. A device that suddenly begins communicating with an unusual IP address or sends an abnormal amount of data could be flagged as an anomaly. Tools like scikit-learn in Python offer robust libraries for implementing clustering algorithms, providing a practical framework for cybersecurity professionals. Dimensionality reduction techniques, such as principal component analysis and t-distributed stochastic neighbor embedding, are also invaluable. These methods reduce the complexity of data without losing its essence, making it easier to visualize and detect anomalies. For example, PCA can transform high-dimensional network traffic data into a two-dimensional plot, where outliers become visually distinct. TensorFlow, an open-source machine learning framework, integrates these techniques, allowing cybersecurity professionals to pre-process and analyze network data efficiently. Another significant unsupervised learning approach involves using neural networks, specifically autoencoders. Autoencoders are designed to learn efficient codings of input data, and when applied to network traffic, they can reconstruct normal traffic patterns. Anomalies are detected by measuring the reconstruction error. Significant deviations between the input and the reconstructed output indicate unusual activity. Implementing autoencoders using frameworks like Keras, which is built on TensorFlow, provides a practical approach to anomaly detection. By training an autoencoder on normal network behavior, deviations can be quickly identified, offering a proactive defense mechanism. Implementing these techniques in real-world scenarios involves several steps. First, data collection is paramount. Network traffic data, including IP addresses, port numbers, and packet sizes, must be collected and anonymized to ensure privacy. Tools like Wireshark can capture network traffic, providing raw data for analysis. Once collected, data preprocessing is necessary to handle missing values, normalize data, and convert categorical data into numerical formats. Python libraries like Pandas offer extensive capabilities for data manipulation and cleaning. After preprocessing, feature extraction is crucial. Feature extraction involves selecting the most relevant data attributes for analysis, which may include time-based features, content-based features, and traffic-based features. This step is essential for reducing data dimensionality and improving algorithm efficiency. Feature selection tools within scikit-learn can assist in identifying these key attributes, ensuring that the model remains both effective and efficient. Once features are extracted, the next step is model training. Depending on the chosen algorithm, models are trained using historical or simulated network traffic data. In clustering, for instance, the model learns typical patterns of network behavior, while in autoencoders, the model learns to reconstruct normal traffic patterns. Training these models requires careful tuning of parameters, such as the number of clusters in k-means or the learning rate in neural networks. This tuning process is often iterative, involving trial and error and cross-validation to ensure model robustness. Deployment of the trained model is the next logical step, and it involves integrating the anomaly detection system into the network infrastructure. This integration must be seamless to avoid disrupting normal operations. Once deployed, the system continuously monitors network traffic, flagging anomalies for further investigation. Integration with existing security information and event management systems can enhance response capabilities, allowing for automated alerts and even preemptive measures to mitigate potential threats. Case studies underscore the effectiveness of unsupervised learning in cybersecurity. For example, a study conducted on a large financial institution demonstrated how clustering algorithms could detect insider threats by identifying unusual access patterns to sensitive data. In another instance, an e-commerce company employed autoencoders to monitor network traffic, successfully identifying and mitigating a botnet attack that traditional security measures had missed. These real-world applications highlight the potential of unsupervised learning to enhance network security and protect against evolving threats. Statistics further validate these methods' efficacy. According to a recent survey, organizations using unsupervised learning for threat detection reported a 30% increase in the identification of previously unknown threats. Moreover, the implementation of these techniques often results in reduced false positives, which is a common drawback of traditional rule-based systems. This improvement not only enhances the accuracy of threat detection, but also boosts operational efficiency by reducing the time and resources spent on investigating false alarms. Despite the potential benefits, challenges remain. Unsupervised learning requires substantial computational resources, particularly for processing large volumes of network data. Additionally, the absence of labeled data complicates model evaluation, as measuring performance without a ground truth is inherently difficult. Overcoming these challenges necessitates a combination of technical expertise and strategic investment in infrastructure. Emphasis on continuous learning and adaptation is crucial given the ever-evolving nature of cyber threats. In conclusion, unsupervised learning offers a promising avenue for identifying anomalous network behavior, providing cybersecurity professionals with advanced tools to detect and mitigate threats. Through clustering, dimensionality reduction, and neural networks, these techniques enable the identification of outliers and unusual patterns indicative of potential security breaches. Practical implementation involves data collection, pre-processing, feature extraction, model training, and deployment, with tools like scikit-learn, TensorFlow, and Keras offering valuable support. Real-world applications and statistical evidence underscore the effectiveness of these methods, while ongoing challenges highlight the need for continuous adaptation and resource investment. As cyber threats continue to evolve, leveraging unsupervised learning is an essential strategy for maintaining robust network security.